But otherwise, I don't think Mr. Althouse needs much of an introduction. Good to go.
Thank you. So, yeah. If you've ever sat through a Salesforce presentation, this is the corporate slide deck. I'm sorry. Um, so about Ben, he works on Salesforce's detection cloud or threat detection team. He's remote from Brisbane, Australia. He's one of our principal engineers. He's really into data visualization and robotics. He actually built a robot guitar that would play firewall logs. That's pretty badass. Yeah, I don't know. I'll put it. I'll find it and I'll post the YouTube for it. But anyways, I'm not Ben. I'm John. That's Ben. So Ben wasn't able to be here, so I'm presenting his slides for him. So if I screw up a little bit, I'm sorry. So I'm gonna go over what is Hash, how it works, some experiences with it, and some different tools that we've developed for it, as well as some use cases. So some background: Hash is a fingerprinting technique for SSH. So here's the background of like fingerprinting over the network. So Fingerprint TLS by Lee Brotherston inspired JA3. JA3 inspired Hash. Hash inspired Bro Sysmon, and so on. And so as people are creating things and open sourcing them, it inspires new things, and that's why we do it. It's great. So Hash, no one. So if I go back here, like no one in the fingerprinting space has it, at least as far as we could tell, open sourced any sort of tool for fingerprinting SSH. So nothing really existed there. So that's why this came about. Ben was excited by JA3, which is fingerprinting for TLS communication, and he was looking at SSH packets in Wireshark, and he saw some anomalies, and he was like, "Hey, I could apply the same technique for SSH," and it worked. So here's how it works for a SSH connection. First, there's the TCP three-way handshake. Immediately following that is the server and client identification string, and this is just ASCII. It's whatever the server wants to say. Usually, it's the version of the SSH client or the SSH server. And then following that is the SSH key exchange init packet, which has all the details on what the client or the server wants to communicate using, which encryption algorithms and etc. And yeah, go ahead. Great question. So, so is this in a specific order? So, kind of. So the identification string does come first, and then the key exchange init. However, I've seen the server send the key exchange init first, and I've seen the client send the key exchange init first. I'm not sure why. I'm wondering if after this part they both just send the packets at the same time, and it's just a race condition. But I've seen both. So the server packet could come first, or the client packet. I don't know. So, but it also it doesn't matter. So for the fingerprinting, then there's the key exchange, and then everything after that is encrypted. So this is what it looks like in Wireshark. And this is not like some sort of Wireshark extracting more data and giving you more data. This is literally what it looks like. If you look at the code down here, it's just ASCII. So this is really interesting with TLS. In the client hello packet, it's really well crafted so that each cipher or each extension is represented by just hexadecimal characters. And then that represents an entire huge cipher name. In SSH, they just put the whole name of the cipher, comma delimited, so which is like nowhere near as good as TLS. But it's interesting, and it's just ASCII, and you can put anything in here. I mean, you could put paragraphs of information in there, and it'll just, as long as there's a cipher in there that it can find, it'll just keep working. So that's interesting. So for an example of how this works, we'll use CyberDuck. This is the key exchange methods, the encryption, and the message auth for CyberDuck. This is in the key exchange init packet for the client. And so how hash works is it takes those and the compression algorithms. It takes those four fields, it then concatenates them using a semicolon delimiter, and they're already delimited by commas. So each like cipher is delimited by a comma, and then we delimit each field by a semicolon. We take that entire string and MD5 hash it, and then this is our hash value. This is our fingerprint for the client or the server. Yes. No, we haven't. But we haven't seen it. We haven't tried it. I'm sure it's possible. How? I don't know if it has a size limit. If you're thinking buffer overflow vulnerabilities, you're probably right. Because what was Heartbleed, right? That was basically the same thing. Buffer overflow inside the beginning of the connection. So this, yeah, there's probably some clients that are vulnerable to just loading in tons of information here, but that's not what we're talking about today. Off track. And then also, I want to mention something here. We're MD5 hashing all of this so that we have a nice and easy to use and shareable 32-character fingerprint, same as JA3. And the reason why we're using MD5 is because, well, everything supports it. This is a method. This isn't a program. This is just a method. So you can implement this method on whatever technology you have, whether it be like the oldest NetScreen firewall, whatever it is, it'll support MD5 hashing. Also, 32 characters is just easier to share. You can tweet it with context around it. Originally, Ben wanted to do SHA-256 just out of principle, and it was a 64-character string. And when you try to tweet like a 64-character fingerprint and try to add context, like, hey, look for this thing, and then you run out of characters on Twitter. So I was like, there's no reason for it. We're not going to have hash collisions with this type of data. So MD5, and that's why we did that. So here's some examples, CyberDuck, whatnot. So these are our fingerprints for them. An interesting one is like FTP, SSH 2.0 FTP. So you have some context around an SSH connection going out of your network. You can say, oh, well, this is not just SSH. This is an FTP connection. So if you're running bro and you want hash, you can just do bro package install hash, and you'll have it. This is what it looks like. Ryan. Yeah. Wait, I'm sorry. I'm missing your right. Oh, right. Oh, yes. Yes. So the question is, won't this look benign if someone just uses the SSH client that's natively on whatever client it is, connecting out to the internet? That'll just look like everything else that's SSHing out. The answer is yes. However, there's more capability here, and I'll dive into that. So stay with me. This is what it looks like on Bro. If you're running hash on Bro, I think natively it just comes with the hash for the client, and then the hash server for the server side. And then everything else is optional. If you want to do hunting and you want to gather all that data, you can enable that in the Bro script. Adele Kazemi, who is also on our detection team, wrote a Python module for this. So let's do a time check. Okay, cool. So the Python module, if you're not running Bro, you can use the Python module, which can read PCAP files or listen to live traffic and output the hash values as well. He also wrote this amazing thing where he Dockerized hash and made it so that it would load up different versions of SSH clients over and over and automatically spit out PCAPs and then build an automatic list of like hash to client values. And that code is on our GitHub, which is github.com/salesforce/hash, HASSH. And the list that he already generated is there too if you want to go ahead and play with that. He also, Adele is just like a coding master. So he also wrote an nmap script so you can scan the internet or scan your network and be able to find out what the hash values are for any SSH servers on your network or wherever you're looking. So where this can really shine is in like a highly controlled production environment, right? Where you know that your prod servers should only be communicating over, whatever applications are on your prod server. So if your prod servers are the same versions of operating system with the same, packages installed and everything like that, then you know what you should be looking for. Also, things that are connecting to your prod servers, if it's the Bastion server or whatnot, the Bastion servers, hopefully, and your production network are all the same with all the same version, all the same operating system, so you know what to expect connecting to your prod servers. And if you see anything else, well, then maybe that's malicious. Another example would be like GCP. So with GCP, when you want to SSH through the Google GUI, it actually, hold on, there we go. So it's actually very unique. The way that when you SSH through the GUI, you get an SSH window inside the GUI in your browser, right? But the way that Google does it on the back end is it SSHs using its client. Its client has a very unique method of communicating over SSH. It actually, and this makes sense, it actually only supports a single encryption method and cipher, and basically all of the algorithms. It only uses one, and unlike all of the other SSH clients like CyberDuck or whatever, where they have just this huge list of encryption methods that they support. Google only has one because it's only ever going to communicate to its systems, and that's it. So why does it need to have backwards compatibility? That's interesting. But anyways, with this, you can essentially say, if you're expecting the only thing to ever SSH into these systems is that Google browser client GUI thing, then you can say if any hash is not this, then alert, right? Right. So let's see. So again, if you see like a hash of Ruby going to your prod servers, maybe that's bad. Loosely controlled environments, so non-prod environments, you can just look for things like the hash for like ncrack or some malicious activity. So yeah, ncrack actually is interesting. So ncrack purports that it is OpenSSH version 7.1. It's not. Its hash is very unique and unique to ncrack itself. So if you wanted to detect ncrack, you just look for this hash. That's it. They could say it's like OpenSSH whatever 7.5, the latest version of whatever they want, and this will always remain the same. So this is like your easy detection mechanism. So Cobalt Strike, also easy to detect. Cobalt Strike has a built-in libSSH 2 version 1.7. This is hard-coded in the Cobalt Strike. You can't change what version of SSH Cobalt Strike uses. So that's interesting because you shouldn't expect that version of libSSH to be connecting out from like a Windows host. So if you have a Windows host that has this hash for SSH going outbound to like something else inside your network, then you can assume compromised. So the libSSH auth bypass bug, if you guys remember that was terrible. So it was basically, in the SSH communication, when you send your username and password, that's a auth request. And then if it was successful, then the server's like, yeah, you're good to go. And then the client will send a user auth success. Okay, give me a shell, right? Well, with this bug, instead of sending that request packet, they just send the success. Like, oh, I already sent my username and password. You told me I'm good, so can I have a shell? And then libSSH would be like, okay. So that was a huge vulnerability. That was really bad. So with hash, we could search for that within our network, those vulnerable versions of libSSH. And so it's one thing to rely on the identifier string, but that can easily be changed. It can easily be modified. And so the main concern here is like, what if you have some vendor product in your network that is using this vulnerable version of libSSH, but they change the identifier string to be like super secure, client shell vendor product thing, right? So with hash, we would be able to determine whether or not that is actually the vulnerable version of libSSH. Um, so so if you find a means of detection for, all right, 5 minutes, means of detection for like a successful exploit of this libSSH shell, um, uh, you could look for the hashes of exploit tools, Metasploit uses Ruby, for example, and then the hash server being a libSSH server, you could kind of assume maybe that's an exploit attempt. But if you have the auth logs, you could verify and say this is a exploit successful or whatnot. Um, so here's a problem for Andrew at Grey Noise, is that this is really good at detecting honeypots too. So with honeypots, you could say like, "Hey, I'm this vulnerable version of like a Cisco router, but actually it's the some SSH client that's running on the honeypot." Well, this is able to determine whether or not that is actually what you're saying it is. Which sucks for honeypots, guys. I'm sorry. One of the downsides. So this is also interesting. So Adele was spending some time kind of doing the same thing that Andrew does, looking for or looking at connections coming in to a honeypot that he set up somewhere on the internet. And so what he was seeing was that people were connecting using the hash of Golang, but they were changing their client identifier strings. This says OpenSSH, and then like weird gobbledygook. I have no idea why they were doing that, but this was changing quite often. But the hash remained the same, and so they were scanning, and they ended up creating this giant list of like different client identifier strings. However, the client remained the same, so it was always the same. So. Oh, yeah. He also included a geo map. The big surprise, it's China. Um, so all the scans were from one IP address. The hash values were all the same, but the client strings are being spoofed and cycled through for this scanner, and the account attempts were all root in this example. But yeah, so why? I don't understand why they're alternating their client. Maybe Andrew has some ideas for this, but why are they alternating their client strings as they're scanning?
I see it too, but I mean, my guess is just because a lot of people, myself included, derive a lot of value from fingerprinting those, and it's a very, very brittle way to break those fingerprints. It took me literally 5 seconds, and anybody else who gets fingerprinted. But if you have any kind of clustering, and that is a feature of the cluster, and you're using that to cluster people together, it breaks that until you put 5 minutes of work into it.
Right.
So that's my guess, but honestly, I don't know. It might be some crazy C2 like. That's my guess.
Yeah, probably not. So yeah, so Andrew says that it's most likely that they're just trying to make it so that it's more difficult to correlate a threat actor together, basically. Um, anyways, does anyone have any questions on this? Yes.
What's the entropy? How much like space is there? Like in a when you're doing this thing, how many possible combinations?
There's a huge amount of combinations. Yeah, I I don't know. I don't know what the key space is, but there's a huge amount of combinations for this. It turns out that pretty much every single SSH client and SSH server application has its own unique hash value. We've rarely come across duplicates, or usually the duplicate is because they've increased their version number, they've done something, but they haven't changed the way it communicates. So like yeah. Other question? Yes. Is there a repository of known good, known bad? No, I don't think so. But you could easily create it if you go to our GitHub. Again, that's github.com/salesforce/hash, HASSH. All of the scripts to build that are there. So that's easy. And then we also have that list of basically known clients that is there as well. Any other questions? Okay, just one thing real quick, which I thought was interesting. So this is already built into Gray Noise. Binary Edge, CoWire, Shodan uses this. Trizzle NSM. There's a MISP security onion it's built into, and it is also being deployed on ExtraHop and Suricata. So So if you have any of those, you guys will be able to use this as well. All right, cool. Thank you.